Okay, so good morning everyone. My name is Thiago and I'll be presenting our paper entitled Reward Shaping for Learning the Pre-Skimming Reach Phase with a Robotic Manipulator. Co-authors are me, Hector, and Douglas. We are from the Computer Vision and Robotics Laboratory from UFMG in the Department of Computer Science. So we know that manipulators are well suited for repetitive tasks in structured environments. So if you have waypoints, defined waypoints on a structured environment, nothing is really highly dynamic. Manipulators have been shown to be to work very well in such environments. But classical PID and other types of controllers usually struggle on highly dynamic environments where objects interact with each other and also with the tool and also with uncertain elements like fluids. So for instance, if you have a highly dynamic environment like an industrial kitchen where you have several workers walking around, moving baskets here and there, cooking at the same time, this is a not very well structured environment, and usually robots don't succeed in such environments. Moving forward, we're going to define our main task, and then we're going to show a couple of challenges. So the skimming task can be defined as collecting an object from a fluid. In this case, we see probably a human using a skimming tool, collecting objects, in this case leaves, from the water. So you see that the tool allows the fluid to go through as you collect the objects and remove them from the fluid. Several challenges arise. One of them is that objects tend to drift away as you are trying to go after them. And also, if we're dealing with different types of fluids like oil, water, the viscosity can change, the dynamics change. So you have to do different forces, the dynamics change, so it's a more complex problem. It can be broken down into three main phases. The first one is the approach or reach phase, where you position the skimming tool close to the object, but you don't collect it yet. Then there's the second phase, which is the actual collection phase, where you put the object inside the tool, and then you finally remove it from the fluid. Our work focused on the pre-skimming reach phase, assuming the object pose is known. So reinforcement learning has been widely used and is being used more and more in solving complex real-world problems. And PPO, which stands for Proximal Policy Optimization, has been widely used as well and has shown pretty good success rates on solving real-world complex problems. So here we have an overview of an actor-critic PPO. So on a basic reinforcement learning level, we have the environment, and we're training an agent to interact with the environment. The agent takes actions in the environment, and it reaches a state and it collects rewards. In this case, we have what's called a trajectory memory, where we perform a certain number of actions, we collect a certain number of rewards, and that is used in mini batches to train the actor-critic network. Since we are on a continuous space, we have here neural networks to process all this data. And here we can see that the actor network can be seen as the policy, where it takes action. So given a state, it chooses an action to interact with the environment. And the critic is used only during training to estimate the value function, which tells us how good taking that action at that state is. So here during training, we have RT, which is the policy ratio, which relates the current policy and the old policy. So given a state and an action, how more or less likely is the current policy going to take action A with respect to the old policy? Also, on the critic side, we have the temporal difference, delta t, and that helps us to get the advantage estimate, which tells us how better or worse that action has performed. So we have an estimate of how good that action is. We collect the actual result and we compare that. If the advantage is better, which means that action returned a better result, so we want to increase that action at that state. All of that comes into the loss, which is the main the main difference from PPO to other policy optimization algorithms, which is it clips the result, it clips the step that it does on the actor weights into a certain threshold, so it doesn't spike up and down, it doesn't move too far off. Here in the critic, we have the same thing. We are updating the weights of the network based on the loss. The main difference is that here in the actor network, we're doing a stochastic gradient ascent because we're trying to maximize the returned value. And here on the critic, we usually do a stochastic gradient descent because we're trying to minimize the error from the actual value function. Our methodology has two hidden layers on both the actor and the critic networks. So we use 64 hidden units on each one of them. In our state vector, we have joint positions, velocities, target pose, and the previous action. The previous action helps us in the next step, which is when we define rewards. The actions themselves are continuous joint positions. And we use Isaac Lab with Isaac Sim, which is the simulator and the reinforcement learning framework to train this pipeline. We train a PPO policy for Kinova Gen 3, which is a 7DOF robotic manipulator. We run 4,096 environments on 500 epochs. Here we can see our state vector, so 7 joint positions, velocities, target pose, and the last action taken. So here we have the basic rewards, which we define to do pretty much any sort of reach task. And next we're going to define our novelty and our proposed solution, which brings a reward specific for the skimming task. So here the basic rewards that we consider are position, which means how close the effector is to the target. It's a basic Euclidean distance, and that is defined as the error in position. In the orientation for this work, we define a skimming tool that is symmetrical with respect to z. So actually x and y are not really relevant when we talk about orientation. So we don't really need to orient x and y in the target pose. In the target pose, all we care about is aligning the z-axis, because as I said, the skimming tool will be symmetrical around z. So all we do is to calculate the angle between the two axes and define an error as well. And all of these errors will have either a positive or negative weight when we are creating the whole reward function. Action rate also penalizes high magnitude changes, and that is to reduce jerk. So usually in these types of training, you usually see robots shaking too much with a high jerk. This is used to minimize jerk. And also joint velocity. So we want to reach the target, but we want to respect joint limits, joint velocity limits, and we also want to do a smooth motion. We don't want to go straight to the point and violate joint velocities. And here is our proposed solution and key innovation. So as we think about collecting an object on a fluid, we of course don't want to splash the water, we don't want to create disturbances in the water, and of course we don't want to position the tool above the object to be collected. Like we saw in the first image, we usually come from the sides to collect the object and remove it from the water. So here the main idea is to create a high penalty region in the form of a conical penalty region, which encourages the robot to come from either to the side or below. So this region is positioned right above the target. So this is the position with, relative to the object. So we are at the origin. We define a height h, capital H. We have the radius at height, lowercase h. So what we do is, if we are outside the conical region, of course, we don't want to penalize our agent. If we get inside the cone region, we want to penalize our agent. And the rationale is, the closer you are to the cone axis, so given a certain height, the closer you are to the center, the higher the penalty. And the closer you are to the object, the higher the penalty as well. So we have, so d is the distance from the effector to the cone axis. We take the radius at that height, subtract d, and we get the max between that and 0. So that means if we are outside, we don't have any penalty. And we have delta r and delta h, which penalizes the agent the closer you are to the radius, to the center, right, of the cone, and also the closer you are to the object. And also to avoid super high penalties, we take the max between that and eta, which is a constant that we define, so that we don't have exploding gradients. So about the experiments and results. So hyperparameter tuning requires several experiments, so we had to tune the agent in several aspects, but we brought it down to 3 different experiments where we balance the weight and the penalization on position and orientation. The first experiment penalizes position more, so the further away you are more penalized, so minus 75. Experiment 2 penalizes more the orientation, so the more you are disoriented from the target, the more penalized you get. And experiment 3 is a balance between the 2 weights. What we can see here is, first of all, the expected. So experiment 1 achieves the lowest error in position because we're penalizing position more. So that makes the agent, want to get closer to the object. When we look at the orientation error in Z, the more penalization we do on orientation, the more the agent tries to align the Z-axis. And also, when there is a balance between the two, it usually stays in between the 2 results. So here for the cone penalty, in all cases, it was good enough to make the robot avoid the conical region, as we're going to see. They all have pretty much the same behavior. At first, the agent explores the environment too much. The actions are too random. So then it receives a high penalty. And then it stabilizes at a value close to 0, which means it avoids the conical region. So the resulting behavior learned by the policy completely avoids the cone region, while a classical controller cuts through it. So as you can see here, a PID controller wants to go straight to the point, and it doesn't really care about avoiding the conical region, so it goes straight to the point, whereas our policy completely avoids the conical region because of the penalty that we have enforced. On the left, we can also see, at the left-hand side, we see a classical controller. On the right-hand side, we see the learned policy. I'm also going to show you a video about that. So in terms of cone intrusion, once we consider just what's below the height of the cone, the intrusion drops from almost 60% in the PID baseline to 0% in the learned RL policy, while still keeping position orientation errors acceptable. So the conclusion is that the RL policy was able to learn a smooth and geometrically correct pre-skimming reach motion. We found out that having a heavier position error penalty yielded better overall results because it gets closer to the target without losing too much of its orientation. And the conical region was completely avoided. In future work, we expect to have a sim-to-real transfer, so we really want to test our policy in the real robot. We want to do a full scoop and retrieval, so not just a pre-skimming, but also collect and remove. We want to do fluid simulation and tool interaction, which are pretty heavy to simulate, but it also brings us closer to the real robot. And finally, using domain randomization for variability on the object mass, on the viscosity, on the tool. So all of that makes the policy more robust when we transfer it to the real robot. That's it. Thank you. You have any questions?
Your actor network outputs position vector, right?
Yeah. So basically, the lower level controller is irrelevant for us. We consider that we have a position-based controller where if we just pass the position, the joint position we want to be at, the lower level controller takes care of the rest.
And was some kind of clip for the current position to the other position?
A clip
Yeah, some kind of limits that can.
of the action. Yes, the action is normalized. So you have the maximum ranges of each motor, and then you normalize that into 0 to 1 or -1 to 1, and then you either apply a small, positive or negative value with the respect to the current position.
And was any specific reason for doing this for position instead of velocity or acceleration?
It's a good question. Well, for simplicity, working with like position in this case and also in the simulation and the reinforcement learning framework, Isaac Lab, it's easier to do that way. So I guess for simplicity, yeah. Thank you.
My question has been answered right now.
Really?
Thank you very much.
Okay. And this is just a simulation showing here is our policy, which completely avoids the cone region, and here is a classical PID controller, which goes exactly through the cone. Yeah. And Z is pointing forward, so both of them are trying to align with Z. So Z is pointing forward, so we can see, yeah. So this is PID, this is reinforcement learning. Yeah, that's a great question. So we were using Isaac Sim and Isaac Lab as our framework and simulator. And I was talking to Armando just before we get started. Simulating fluids yet in Isaac Sim and Isaac Lab is pretty hard. They are currently, like right now, integrating the warp library, which is NVIDIA's library for fluid simulation and other types of aerodynamic simulation. So they are implementing this now. So unfortunately, I couldn't use warp, which is this library, to simulate fluid as I wanted, right? And this is also a work from last year, right? We ended up switching to the Genesis simulator, which has a simpler simulation for fluids, but that works and is already, able to take tests. So that's why we started working with actual fluids after this paper, and we are currently working on it. We intended to use warp, as I said, but it's still under development. It's crashing too much. It's giving too much headache, so we ended up switching.
We are using static fluids. Static fluids.
For this, yes.
Do you think dynamic environments will
They will be much more difficult, especially if you add not only the dynamics but also the fluid itself. Like the tool will have to interact with the with the fluid, remove it. So that makes things a lot harder.